Professor, welcome, Professor. Professor. Professor, welcome. Professor, good morning.
Good morning, good morning. I was muted, so.
Okay. How are you?
I am good. I am good. How are you? We have a nice weather.
Yeah,
Everything
fine,
good?
Professor. Thank you for accepting our invitation.
You are welcome.
Meet my colleagues, Dr. K. Subramaniam, sir. Subramaniam,
Yes.
sir.
Okay. Yes. Nice to meet you.
Subramaniam, sir.
He is muted.
Yeah. And meet Dr. Beena. Beena,
Dr.
sir.
Beena,
Yes,
nice
sir.
to meet you.
Morning,
Nice
sir.
to meet you.
Good morning, sir. Myself, Dina. Yeah, thank you, sir. Welcome, sir. Welcome.
Perhaps we can try the screen sharing.
Yes, sir. Yes, sir. You can try once. We will see. Yes, Professor. Your screen is visible. Yeah, fine.
The screen is visible. Very good.
Yes,
Wonderful.
Professor. Thank you. Thank you so
very
much.
much. Thank you very much. So maybe you can explain to me the purpose of this of these meetings.
Okay,
I see that there are many people lecturing, and I wonder what is the interest on your part.
Our HOD has entered, Professor. HOD, ma'am.
Sorry?
Yeah, our head of the department.
Okay. Yes, but what is the purpose of these meetings? I don't. Okay. Who is in the audience?
Yes, Professor. She will soon become co-host.
But who is listening to these presentations? Who will be in the audience?
Research scholars, faculty members, and research associates, Professor.
Mm-hmm.
Good morning, Professor.
Good morning.
I'm Sudha. How are you?
Nice to meet you.
How are you?
Good. I am good. How are you?
Yeah, fine.
This is evening in Chennai, isn't it?
Yes. 7 o'clock, 7 p.m.
7 p.m. Very good. Okay, I guess we have a few more minutes.
எப்படி போட்டோ எடுக்குது உங்களோட செல்ல போட்டோ எடுத்துருக்கு ஹோம்ஒர்க் போட்டோ எடுத்து அனுப்பிச்சிட்டோம்.
Professor, how is the situation in Canada, Professor?
Yes.
This
The
COVID
situation?
how it is?
Are you asking about the pandemic?
Yes, Professor. Yes.
Well, we are yes. So we are in the middle of the fourth wave.
Fourth wave.
Fourth wave. Yes. At the moment, some class. So as far as university is concerned, everybody on campus has to be doubly vaccinated. And we have some in-person classes and some online classes.
Yes.
So I am teaching in person, but it's a relatively small class. And so in a large room, everybody is supposed to wear masks. The number of infections is growing with every day. So we will see how it goes.
Still now it is growing only.
Pardon me?
Still now it is growing. In
Yes,
fourth
it
wave
is,
also
it is growing. It went down, and now it's growing again.
Okay. So,
I mean,
Canada is not allowing international passengers.
I think it is now it's allowing international passengers, not from every country. So I am not sure what the situation with India.
From India, no.
No flights from India.
Yeah.
I was a week ago, I was in Switzerland. So passengers from Switzerland are allowed. But yeah, I don't know all the restrictions.
From India, they go to Maldives, then Turkey, then Canada.
Okay. Yes. This is some provinces. Some provinces have are in a critical situation. Alberta.
Yes, that is why.
Alberta is in a critical situation. Their health system is strained, and they just ask for military help. So, yeah, they relaxed too early.
But the percentage of those who vaccinated is much more.
I think right now we are reaching 80% vaccinated, doubly vaccinated. So, 20%, it's still a significant, significant number of people. And of course, the hospitals are not prepared for the entire population or large fragment of a population to be sick. So it's a tragedy for other people who are waiting for heart surgery, for cancer treatment, for emergencies. It's really terrible. And how is it in Chennai?
Chennai, okay.
Okay.
We have asked the students to come today.
Mm-hmm.
And 80% of the students have reported. But we don't know how it will be, how we will be able to manage, because some students are staying in hostel.
Mm-hmm.
We are following the guidelines issued by the government.
Mm-hmm. And what is the percentage of vaccinated population?
70%.
70%. That's great. That's great. That's very high. Okay. So it's 7 o'clock.
Sir, Subramanian, sir.
Yeah, Professor.
Yes, ma'am.
With your permission, we would like to portray our recent programs. Can I share my screen, Professor?
Sorry, are you speaking to me or?
Yes. He's speaking to you. Sir,
Yes.
2 minutes, sir. Is it 2 minutes?
2 minutes?
It will take more than 4 minutes, ma'am.
Do you mind?
Do I mind what? Sorry, I cannot
4 minutes video we are going to play. Do you mind about it?
Okay, go ahead. You are playing a video.
Yes, about our department programs.
Okay. All right, very good.
Shall I go, ma'am?
Yes, sir.
Yes,
Yes,
sir.
sir.
Shall we start?
Yes.
Good evening to all.
HOD, madam.
Yes, sir.
Dean sir has come now.
Okay. Good evening, Dean sir. Good evening, Dean sir.
Actually, he's not in the meeting. I think. Subramanian sir,
Yes, ma'am.
I think Dean sir is not in the meeting.
No, he is there.
Sir, no, sir, he is not in the meeting, sir. Dean, sir. Subramanian, sir, he is not in the meeting.
Ma'am, shall I proceed?
Yes, ma'am.
Good evening to all. I welcome you all for the day 8, session 10 of 2-week International Faculty Development Program on Advanced Computational and Experimental Research in Physics 2021, organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram Campus, Chennai. SRM Institute of Science and Technology is one of the top-ranking universities in India with over 38,000 students and more than 2,600 faculty members across all the campus, offering a wide range of undergraduate, postgraduate, and doctoral programs in engineering, management, medicine, health sciences, and science and humanities. The institute has academic tie-up with leading foreign universities like MIT, University of California, USA, and University of Dundee, Oxford University, UK. Our institute is accredited by NAAC with A++ grade in the year 2018 and got placed in A category by MHRD. With this, now I request Dr. L. Sudha, Professor in Department of Physics, SRM IST Ramapuram Campus, to give the welcome address. Ma'am, please.
Yes. Thank you, Dr. Beena. Good evening, all who have joined this 2-week International Faculty Development Program on Advanced Computational and Experimental Research in Physics 2021. I take privilege in welcoming Dr. Paul Horlock, Professor, Department of Physics, University of Ottawa, Canada, for accepting our invitation to deliver a talk on designing materials at the nanoscale. Thank you, Professor, for accepting our invitation and to spare your valuable time with us today in spite of your busy schedule. And today is a day 8 and session 10. And today we had one more talk also by Dr. Manirajan, who delivered a lecture on photonic crystal fiber for biosensing applications. Hope and I extend a very hearty welcome to all the other participants who have been attending all our sessions and all our programs. Hope all the lectures delivered by the eminent persons will benefit all of us. Thank you.
Thank you, ma'am. Now I request Dr. V. Jayalakshmi, Assistant Professor, Department of Physics, SRM IST Ramapuram, to introduce our resource person. Ma'am.
Good evening to all. I feel proud and privileged to introduce Dr. Paul Horlock, University Research Chair in Quantum Theory of Materials, Nanostructures and Devices, Department of Physics, University of Ottawa, Canada. So his area of interest are computational design of materials at nanoscience, graphene, carbonics, 2D crystals and topological insulators, electronic and optical properties of semiconductor, nanostructures, strongly correlated electrons, quantum information, nanoelectronics, nanospintronics, nanophotonics, other areas of theoretical condensed matter physics. He has completed his PhD in condensed matter theory, University of Kent, USA. He completed his MSc in Wrocław University, Poland. He has contributed his research contribution from 1984 to till now. He is a professor of physics and university research chair in quantum theory of materials, nanostructures and devices from 2014 to till now. So he has worked as invited professor, World Premium Institute of Advanced Materials Brain Drain Program in Japan from 2013. And he worked from 2012 to 2014, group leader, quantum theory of group, security and dispute technologies, emerging technologies division, National Research Council of Canada, Ottawa. Research experience are more. So due to time lag, I have stopped this. He has more than 200 publications in highly reputed journals. He is a member in many of the international, he has been a member in many of the international advisory boards in USA, Israel, Poland, Japan, Italy, Argentina, Russia, France, China, Mexico, etc. He is an editorial member of in Solid State Communication elsewhere in 2013. He has been co-director in many of the symposium organized in Canada, Poland, Lyon, etc. His awards are many. So due to time constraint, I'm going to point out few. He got gold medal with diamonds in Wroclaw University of Technology. He got Queen Elizabeth Diamond Jubilee Medal in contribution to Canadian science. He won Canadian Association of Physicists Wroclaw Medal for outstanding contribution to condensed matter physics in 2002. In 2003, NRC Outstanding Research Achievements Award for the development of single spin transistor. Professor, we are very grateful to welcome you here, and we are blessed to hear your lecture, Professor. I request you to take over the session.
Thank you very much, Professor Jayalakshmi, for your kind invitation and the introduction. So I see that that the Institute had a very, very broad set of lectures in various programs. I will just try to tell you a little bit of what we are doing in Ottawa. I will be talking about material. I will be talking about materials at the nanoscale, and many of my collaborators contributed to this work. I listed most of them here. So let me see. So we are in Ottawa, and this is a view from not far from the campus, from the physics building on the downtown Ottawa. You see here Rideau Canal, you see the Congress Center, you see the hotel Chateau Laurier, and you see here the towers of the Parliament. So
Professor, sorry to interrupt you, Professor. Your screen is not visible to us.
My screen?
Yeah, you didn't share us. Share it.
Okay, I did share it. We have been able to see it, but okay, I don't.
We are able to see you, but not your screen.
Okay, let's see how to do this. Okay, share screen one more time. Here it is. Okay, and now? Can you see this?
Yes.
Screen is full screen, Professor.
Can you make it full screen?
Yes, I am trying to. Yes. So let me go. Let me go back. So these are my collaborators, and I will acknowledge them at the end also. And as I said, we are in Ottawa, and this is a view not far from the campus. What you see here is a Congress Center. On the left, National Arts Center. This is a Rideau Canal that flows into the Ottawa River through a series of locks. This is a Chateau Laurier. It's a hotel, formerly a hotel of Canadian Pacific Railway, and these are the towers of Parliament. So it's a nice city. If you have a chance to visit, please let me know. Okay, so how can I do this? Okay, so in designing materials, the main challenge, there are several challenges, and one of them, perhaps the biggest, is that there are many electrons in a solid, in a material. And I will explain what the challenge is. So imagine that that an atom is depicted here as a little square, and that an electron is assigned a number 1. And then if we get a quantum solid, it consists of several atoms. In this example, we have an array of 12 atoms and 1, 2, 3, 4, 5 electrons. Yes? So this is a very small solid. How many configurations can we have in this model solid? Well, about 800 configurations of electrons. And so the space of these configurations is the Hilbert space. And if I just increase the number of the solid by a little bit, from 12 to 24, the number of electrons from 5 to 10, I will get about several million configurations. And if I increase this number of a solid by a factor of 10, from 24 to 240, and the number of electrons from 10 to 100, I get about 10 to 70 configurations. So some people say that about 10 to 70 is the number of atoms on Earth. So clearly we are generating a huge Hilbert space, and this is a great challenge. This is a great challenge that we still don't know how to solve, how to handle. This also is a great opportunity, because with a small number of bits of information, the number of these atoms, we have a tremendous number of resources. And that's why we often think of these model solids also as quantum registers. So we have a challenge and we have a potential opportunity with purely quantum mechanical many electron systems. So we have this huge Hilbert space of material, and clearly this was just a very small model system, and real systems are much bigger. So how can we possibly solve this problem? Well, I think over the last, 20 years, we made some progress, and this progress can be summarized by noting that in many systems, the interactions are local. So for example, what do I mean by that? If I have a spin at site 1, it interacts with a spin at site 2. A spin in site 2 interacts with spin at site 3. So we have local interactions.
Hello.
Yes. So we have local interactions. And for gap system, at least, there is something called entanglement entropy law, which says that entanglement of a large subsystem can be divided. The large subsystem can be divided into a relevant part and part A and a part B, and the entanglement grows with the boundary of this selected region. Yes? So it's local, and therefore we can learn something about small pieces of the Hilbert space. So only small portion of Hilbert space becomes relevant, and out of this 10 to 70 configurations, we have a manageable number that contribute to physical properties of the system. So that means that the situation is not completely hopeless. So this was a challenge, a fundamental challenge in our understanding of many electron systems. But there are other practical challenges. For example, a challenge associated with energy use of electronics and photonics. So critical challenge in these electronic systems is power dissipation. And this seems to be completely removed from the problem of large Hilbert space, but it all comes down to the same problem. So power dissipation, if you to illustrate the size of the problem with power dissipation, we can ask how much energy is used in a 10-minute Google search. So if you do Google search, yes, for Ottawa, Canada, couple minutes, yes, how much energy do you think you are using? Well, in this non-interactive form, of course, I don't see raised hands and everybody telling me that energy for a 10-minute Google search is the same as boiling cup of water. Okay, I think at least some of us who are a little older remember how to boil water, and so boiling a cup of water is a lot of energy. So the problem of energy is, of course, critical in current electronics. Why do we have this problem? We have this problem because current semiconductor information and communication technology relies on many different materials. For example, electronics relies on or is implemented with silicon. Okay? Optoelectronics is implemented in compound semiconductors, mainly indium arsenide, indium phosphide based. Yes, and at least standard classical memory is based on ferromagnets. So we have these very different materials, and of course they are connected and they use a lot of energy. There is another aspect of why we need to think about designing materials at the nanoscale. That is sustainability. So if we look at these different materials and we look at the abundance of materials in the crust of Earth, then we see that silicon is very abundant. Yes, carbon, there is also lots of carbon. But there is a class of materials which become rare and increasingly rare. And here is gallium arsenide. So all your CD players use lasers based on gallium arsenide. You have the indium phosphide for optoelectronics, and this borders on very rare elements. Yes? So some of the materials that we currently use in information and communication technologies are rare. So the current semiconductor technology uses many materials and is therefore not sustainable, is energy inefficient, and it's not powerful enough in solving many of our problems. So we have been working on a number of problems which can be illustrated with these pictures, and we will talk a little bit in greater detail in some of them, but this will give you a summary of our activities, and I think the audience is very broad, so perhaps there will be questions related to some of these problems. So one activity in our group is related to quantum circuits based on electron spin. So if you have electron spin up and down, it's a qubit, and we have been building quantum circuits made of individual electrons. So what you see here is a surface of gallium aluminum arsenide. You see here metallic gates, and what is underneath are individual electrons which are localized and operated on individually to realize quantum circuits. We have also been working on sources for entangled photons, so single photons and entangled photons. And this is a picture of a schematic picture depicting a indium phosphide nanowire, which with a emitter, quantum dot, indium arsenide quantum dots inserted in the middle. So this is a way to build a source of entangled photons, and also a way to build a spin-photon interface. If we have quantum information stored in individual electron spins, then we need to convert this information into photons, and that's a vehicle that we are using. Then we have we have been working on self-assembled quantum dots. So in these structures, we can grow a single nanowire, a single quantum dot in a specific position with specific parameters. For many applications, we don't need these individual quantum dots. We have arrays of randomly assembled quantum dots, and they are self-assembled quantum dots, and they are used for quantum dot lasers. So this is a cross-section, this is a model schematic picture of an indium arsenide quantum dot embedded in gallium arsenide, and this is a cross-section of such a structure obtained with transmission electron microscope several years ago. Then we have another area of research on nuclear spintronics. So most atoms have nuclear spin. This nuclear spin is invisible in current technology, but if we learn how to manipulate this nuclear spin, then we have another important resource for quantum information processing. And this is a picture illustrating such a single spin in a quantum dot. This time it's a cadmium telluride quantum dot with a manganese atom inserted into it, but it can be nuclear spin C13 in C12, for example. So another class of materials which we try to design involves topological insulators. So as we know, topological insulators are characterized by, in their non-trivial state, by states localized at the edge. And here is an example of a material we have been working on, mercury cadmium telluride. Perhaps if there is time, I can discuss properties of quantum dots in this material. So all these nanostructures which we have been working on involve a relatively expensive growth. Yes, they require molecular beam epitaxy, this particular structure, chemical beam epitaxy. And of course, there is an interest in a class of materials which are very inexpensive. So printable, that can be printed, and circuits can be made out of, printable circuits can be fabricated. So here we are looking at nanocrystals for photovoltaics, light emitting diodes. We are working on graphene for printed electronics and truly two-dimensional semiconductors such as molybdenum disulfide or tungsten diselenide. So this covers a large area of research within our group, much of it in collaboration with experimentalists. So to design these quantum materials at the nanoscale, we are facing challenges. And one challenge is that these quantum nanostructures in reality involve millions of atoms. Millions of atoms, what is a million of atoms? Well, 10 to 2 times 10 to 2 times 10 to 2 is 10 to 6 atoms, yes? So just 100 atoms in one dimension, and already we are arriving at a million atoms. So electronic properties cannot be calculated using ab initio methods. And so some other ways have to be devised. And also in these nanostructures, we have emergent quantum phenomena. So the properties, what are the emergent quantum phenomena? Properties of material cannot be inferred from properties of its constituents, yes? So properties of a superconducting aluminum cannot be inferred from a metallic phase. So charge and spin fractionalization is an example, and I will go through several such examples. So what do we do in the group to address these physical systems that I described on previous page? Well, we do computational design. We use density functional theory as a tool. We use our own Q-nano tool, which combines, well, I will describe it in a moment, that allows us to address this problem of million atoms. We have a tight binding Hartree Fock CI tool, and we use a concept of quasi-particles. So one way of addressing this challenge of so many atoms and so many electrons that we cannot possibly solve exactly is through the concept of quasi-particles. And I will illustrate this concept on one example. So this is a structure which I already showed. So this is our model of an indium arsenide, gallium arsenide quantum dot. So what we see are indium and arsenic atoms, one in blue, one in red. Yes, and it is surrounded by a different material. And here, before it is surrounded by a different material, it was cut and the transmission electron micrograph was taken. What is it good for? Well, it is an example of excitonic artificial atoms and is used by my colleagues at NRC for quantum dot lasers, making quantum dot lasers. But this is again, the whole structure is many millions of atoms, and so how can we design such a complex system? Well, it turns out that if I put, so there are 10 to roughly here, if it is a solid, there are 10 to 24 electrons. Yes? And imagine I put one extra electron into this structure. So I am throwing one extra electron. It turns out that this one extra electron immersed in 10 to 24 electrons can be understood in terms of a quasi-particle. So a quasi-particle is a means that I can replace this electron by quantum, so by two bosons, which are two harmonic oscillators. And that if you apply magnetic field, you can tune these two harmonic oscillators. And so how do you verify? Well, we prepared the samples and measured these harmonic oscillators in high magnetic fields in Grenoble and Toulouse. And this is a spectrum of these two harmonic oscillators as a function of magnetic field. So these are the levels of two harmonic oscillators, S-like, 2P-like, 3D-like, and so on, shells of two-dimensional harmonic oscillators. So this is we are condensing a very complex physics of 10 to 24 electrons to a model system of two harmonic oscillators with controlled frequencies. Well, sometimes we are not so lucky. So this is a very good starting point, these two harmonic oscillators, but we want to understand all the properties. All the properties of our materials. And to do this, we compute the properties using our computational platform for million atom nanostructures, which we call QNano. So QNano consists of several steps. The first step is we define the structure. So we define the shape, the composition of atoms, where each and every atom is. So for example, we start with indium and arsenide atoms in positions of gallium arsenide. Then we calculate atomistic strain. So we calculate total elastic energy and determine where these atoms really are. Then we use a lot of ab initio input to compute one electron properties. And the nice thing is that we do this in atomistic tight binding scheme, but also in K.P, in effective mass, so that we have different levels of approximation for one electron properties. And already, while strain calculations can be carried out up to about 1 billion atoms, the electronic properties are limited to something of the order of million atoms, with about 20 orbitals for sp3d5 S star. This is about 20 orbitals per atom. And this is a fairly complex calculation in itself. And then what we do is we compute the many-body Hamiltonian, so Coulomb matrix elements, and then use configuration interaction or various other combinations of configuration interaction to compute some small number of quasi-particles, excitons, additional electrons, and then the output is used to calculate response functions, so high bias transport or high excitation optics, or multi-exciton generation for solar cells or Auger processes. So physical properties of these structures. So we go from a billion atom physical description to response functions of our nanostructure. From a billion atom to several quasi-particles, and this is a complex for this small number of quasi-particles. As I explained, this is truly quantum mechanical. The Hilbert space becomes very, very large, and Coulomb matrix elements are a real bottleneck. You can imagine that if you have a single particle state that spanned over 1 million orbitals, then to calculate a single Coulomb matrix elements, you have to multiply 10 to 6 by 10 to 6 by 10 to 6 by 10 to 6. Yes, and that is a very complex calculation. Okay, so we have this tool. We have the concept of quasi-particles. We have these numerical tools, and let me illustrate how we employ these tools to solve to solve problems. So one problem is has been around in nanocrystals for printed electronics and lighting. And the challenge in this field was realizing population inversion. So we had these nanocrystals, they were emitting light, but you could not make a laser out of them. Yes? And the reason for this, as it turned out, was band degeneracy and Auger processes. I will only talk about band degeneracy here. So if you take a cadmium selenide nanocrystal as a function of its diameter and calculate the spectrum of the top of the valence band of this nanocrystal, then you see that this nanocrystal has the top of the valence band has a band of closely spaced levels. Okay, so it's not just an electron confined to a spherical potential. It has a band of states at the top of the valence band. So the hole created at the top of the valence band is spread around many levels, and so only a fraction of a hole can be assigned to the top of the valence band. So with these highly degenerate top of the valence band, the chemical potential of the holes is somewhere in the gap, and so the difference between the Fermi level of electrons and holes is smaller than the gap. Now the gain condition is that this difference in energy levels is larger in the gap. So this red level, the chemical potential of the holes, needs to be brought into the top of the valence band. So with this condition, gain condition, we realized that we need to remove this band degeneracy, and this would lead to a separation of these energy levels, and now the electron and a hole will be localized on a single level, and we will have a nice population inversion. So this is accomplished by strain engineering, and the strain engineering proceeds through facet selective epitaxy, and here my colleague Alek Woźny has been essential in doing this. So this is an example of such a non-symmetrical crystal through the facet selective epitaxy, and also a problem of passivation of such a nanocrystal has been resolved, so that in the end a very high quantum yield with an isotropic nanocrystal was achieved, and here is a structure of such a nanocrystal. And here is a result of experimental result of absorbance and photoluminescence. So this is a photoluminescence peak, and before this facet selective epitaxy, the peak was very broad due to this band of states at the top of the valence band, but biaxially strained quantum dot due to this facet selective epitaxy resulted in narrow recombination spectrum because of this removal of degeneracy of the band. And so this is a final result. You see here such a structure pumped, yes, and at the critical pumping power, you see lasing, yes, and this is illustrated here in this graph. So by designing material, by engineering the material, we have been able to demonstrate lasing in nanocrystals. I have maybe 5 minutes, 10 minutes.
Yeah, you can take 10 minutes.
Okay, so please let me know when I am over time, because we had introductions and all of that. So I will I will cover the carbonics. So one of the challenges in optoelectronics over the last 20 years, maybe even 40 from 70s, has been designing materials with desired band gap. And here is a standard tool in any such a design toolbox. This is a band gap of a material as a function of lattice constant. And so, for example, you can take aluminum arsenide and gallium arsenide and bring them together, any combination of those, with almost the same lattice constant. But indium phosphide and indium arsenide, if you want to have a compound semiconductor varying phosphine content, yes, then you are building strains. So one is limited in designing materials by building up of strain. So can we design optical band gap that does not involve this lattice constant constraint? And we will try to do this with graphene quantum dots, and perhaps demonstrate smooth transition from UV to terahertz within a single material system. So there is a long history of a band theory of graphene. Actually, the paper was called Band Theory of Graphite, and it was developed at National Research Council of Canada, not far from Ottawa, in Chalk River Laboratories in the 40s. And already then, Wallace predicted the closing of energy gap and the linear dispersion of quasi-particles close to the Fermi level, which then were called Dirac fermions. So there is a difficulty in addressing these materials, and that's related to electron-electron interactions. If you take Schrödinger fermions and you assign a little area per electron characterized by a radius of this circle Rs, then we can write the Hamiltonian for Schrödinger electrons, and it will have kinetic energy and it will have interaction energy, and the ratio of interaction to kinetic energy is proportional to Rs, to the distance. Yes? So at large Rs, Coulomb energy dominates. At small Rs, dense material kinetic energy dominates. So we can tune the properties of materials, the role of electron-electron interaction by density. However, yes, so this is the Rs. However, if we look at the two-dimensional gas of Dirac fermions, then we have linear dispersion. And so this parameter that controls the ratio of Coulomb energy to kinetic energy does not depend on density, but it depends on the Fermi velocity and the screening provided by the surrounding material. So we are, it does not depend on density. We are ignorant for any density about the properties of this material. Okay, so how can we design and understand optical band gap? Well, we take a piece of graphene, we make a graphene quantum dot, and now we ask whether it interacts with light. So here are the energy levels of an electron in such a nanostructure, and there is a gap across the Fermi surface, across the Fermi level, Dirac point. Then we shine light and we ask whether there is a dipole moment that connects the occupied state in the valence band with an empty state in the conduction band. And the answer is positive. So graphene dot absorbs, emits light. And of course, only photons with energy larger than this band gap are absorbed. So this is our semiconductor. We went from a semi-metal to a semiconductor. This is our dot energy structure and the gap for a particular size, and then we compute this band gap for different sizes all the way to several million of atoms. And we see that we vary with T of the order of 3 electron volts, we vary the energy of the band gap from UV to terahertz. So clearly we could use such a structure for photovoltaics with highly tunable band. Now, if we compare this band gap of graphene quantum dots with other materials, here is a comparison with silicon, with indium arsenide quantum dots, with lead selenide quantum dots. And so perhaps here would be terahertz quantum cascade lasers. So perhaps we could replace all known optoelectronic materials by just smoothly varying the size of graphene quantum dot. Now, this behavior, the behavior of the band gap with number of atoms can be understood in terms of confined Dirac fermions, and this behavior at small sizes is can be understood in terms of Lieb lattices. I will not go into that, but we understand how this works. 23, so then we have at our disposal not only size but also shape engineering, and I will discuss this in terms of building a synthetic quantum Hall system. So if I take this quantum dot and it's hexagonal-like, and you see this energy spectrum, it's sort of equally spaced energy levels following our linear dispersion. But if I deform our quantum dots, something amazing happens. Energy levels close to the Fermi level collapse to a degenerate shell. And this degeneracy of the shell is proportional to the number of atoms at the edge. And such a degeneracy implies magnetism, implies electronic correlations, and perhaps fractional quantum Hall effect at zero magnetic field. So we study it in a very complicated manner because of degeneracy. We, of course, cannot do perturbation theory, so we have to do exact diagonalization study, and to illustrate the physics, let me show you the energy gap of n added electrons into this degenerate shell. So the degenerate shell, one more time, resembles degenerate states of the Landau level. So here, if I am adding electrons into the degenerate shell and there are no interactions, the gap because of the degeneracy is zero. So nothing is visible here. And if I turn on interactions, I see that the gap oscillates just like in fractional quantum Hall effect. And so gap varies with filling of the shell. It's largest at half filling, and this corresponds to a magnetic moment of this graphene structure. So this was when we examine the triangular structure, it turns out that it consists of two unbalanced sublattices, and the difference between these number of atoms in the two sublattices is responsible for build-up of the magnetic moment. So the spintronics, the magnetism of these structures rests on Lieb's theorem, and Lieb's theorem states that a Hubbard model on bipartite lattice has a ground state spin proportional to the difference of these red and blue atoms. So not only can we design material with desired optical properties, but also with magnetic moment. And so this opens the possibility of integrating electronics, photonics, and spintronics in a single material, graphene. And so this opens the possibility of a new branch of electronics, perhaps called carbononics. I will stop here by drawing your attention to a nice review for the descent of how these graphene quantum dots evolve with size, what are the electronic properties, and what are the electronic properties and what they can be used for. So I try to illustrate how we are addressing challenges, fundamental challenges and practical challenges through designing materials and devices at the nanoscale. And we do this in terms of new materials, for example, 2D crystals, their new functionalities. I talked in some detail about nanocrystals for printed electronics and lighting. I talked a little bit about possibility of carbonics. I did not talk about macroscopic quantum states in semiconductors. I did not talk in any detail about nuclear spintronics. I did not talk about 2D materials nor topological insulators, but this is more than enough. So I want to thank my collaborators for their contribution to this work and you for your attention. Thank you very much.
Thank you, Professor. Thank you so much. Professor, I have a doubt. Actually, I have worked during my PhD. I have worked in tight binding LMTO method. I have worked to calculate the electronic band structure. Can we apply that to nanoscale, Professor?
Yes, that with an input from ab initio, yes. you can using Vanier functions, you can determine the appropriate tight binding model. Absolutely, this is what we are doing here too.
And also now I am using VASP, Professor, to calculate the structural stability and all.
Yes, we are using Abinit VASP, but that is only possible for relatively small structures with hundreds of atoms. You cannot solve the problem of millions of atoms. So it would be nice to do it with ab initio, but it's simply at the moment not feasible.
Okay. Dear participants, if you have any doubts, you can post it in the chat box or you can raise your hand and unmute yourself. You can ask your doubt to our resource person.
Excellent presentation, Professor. Thank you.
You are welcome.
Dear participants, you can post your doubt in the chat box or you can raise your hand and you can unmute yourself and you can ask your doubts. Professor, one more doubt. In VASP, this VASP can be applied to calculate the structure for the nanoscale materials, Professor?
Yes, if they are small, I think something of the order of 100, 200 atoms, you can apply periodic boundary conditions in 3 dimensions, and then you have basically a large molecule of the order of 100 of atoms. Okay. There is, of course, push VASP to larger electron numbers because that's the limiting factor. But it's still of the order of maybe 1,000. That's 1,000 times less than what we need.
Okay.
So what we need is what we do is we do these ab initio calculations for different arrangement of atoms, different sizes, and then compute the parameterize the tight binding Hamiltonian from VASP or Abinit calculations, and now when we have parameterized the Hamiltonian, we can extend it to millions of atoms.
Professor, to designing of the materials at the nanoscale, any particular code is available, or we can use any type of codes we can use it. That is like VAS for Gaussian or TBLMTO or quantum espresso, so many things we are having. No? So any code we can apply, or any particular specific code we can do it to get accuracy in the calculation.
Every code has its limitations, and most codes use pseudopotentials, so your result will depend on pseudopotential. It will depend on your exchange correlation potential. So it will depend on whether you have degeneracies of atomic shells. Yes, then perhaps LDA plus U is a more appropriate tool. I think it's a wonderful progress in ab initio methods, but they really require a careful examination of results. It's not that you can just put any atomic composition and get reliable results. So I think you have to exercise caution.
Yes, Gaussian, Professor.
Sorry?
Gaussian.
No, caution. You have to exercise.
Okay,
you have to be careful with your results.
Okay.
And ideally, also try different computational tools. So compare results in Abinit with results from VASP, and so on.
Thank you, Professor. Really, it is very wonderful, and I think we are all blessed to hear your lecture. Thank you so much for accepting our invitation and giving this wonderful talk. Thank you so much, Professor.
Thank you very much for listening, and thank you very much for your kind invitation. It was my pleasure.
Thank you.
So you have my email, and if there are further questions, I will be happy to answer them on a separate occasion.
Yeah,
Sure.
Professor. Sure, Professor.
Thank you very much. So
yes, ma'am. I'm having this email.
Bye and good luck with your program.
Yeah,
thank you so much.
And now I request Dr. T. Beena to propose vote of thanks.
Good evening to all. It is my privilege to propose vote of thanks for the 8th day, session 10 of 2-week International Faculty Development Program on Advanced Computational and Instrumental Research in Physics 2021, organized by the Department of Physics, SRM IST Ramapuram Campus, Chennai. First of all, I extend my warm thanks to our resource person, Dr. Paul Horlock, Professor, Department of Physics, University of Ottawa, Canada, who gave a very scintillating talk on designing materials at the nanoscale. Sir, it was really informative and effective, and you have clearly explained from the basic to the latest. So it has inspired a lot, sir. And I extend my sincere thanks to our chairman for his encouragement and support to conduct this 2-week workshop. I extend my sincere thanks to our director, Ramapuram and Trichy campus, for a perfect support and guidance extended to us for conducting this FDP. And my sincere thanks to our Dean ENT, Vice Principal Academic, Vice Principal Admin for the support and guidance for conducting this FDP. I thank all the faculty members, research scholars for their continuous support. Last but not least, I'm very much thankful to all the participants who have attended this session. Thank you all.
I'm mute, ma'am.
Yeah. Dear participants, feedback link is available in the chat box. Kindly use it. Subramaniam sir.
Yes, ma'am.
Ma'am, shall we?
Yes, ma'am. Yes, ma'am.
Sir?
Yes, ma'am. Yes, ma'am.
Okay.